is about 6 gigabit, and the bacteria is about 9.6 megabit. Let's make this calculation and let's compare our devices. If we take a DNA size of 9.6 megabit, and we look at it as a non-volatile memory. And the number of RNA per cell is about, this is the memory interface. Remember, RNA is transferring the information from the DNA to the machine. So we have the memory interface of 222,000 bits. Number of cytoplasmic proteins are about 1 million. We can look at them as logic processor, signal processor, and metabolic functions. Ribosomal protein is also close to 1 million. This is our interface because the ribosome is translating the information into proteins. Number of logic devices is 1 million. Number of all proteins about 3.6 million. Time of cell replication is 40 minutes. And what is the energetics? The number of glucose molecules per cell is about in a few hundred thousands. Number of ATP, adenine triphosphate per cell. This is the energy, the phosphate will transfer the energy about 500,000 to 3 million. Total energy stored is 2 picojoule. So the power dissipation is about 1.4 to 10 to the minus 3 watts. So if you compare computers to cells, in cells, the memory is 10 to the 7 bit. In computers, the memory is about, in single silicon, even in the best operation, multi-cell, vertical, we can store like 1,000 bits or maybe 2,000 bits, 10,000 bits. The logic, we can have this number. The power is 10 to the minus 7. The heat is about 1 watt per centimeter square. However, the task time in cells is take 40 minutes. And if you want to do the same task in silicon, it will take much, much longer. And this is, I'm doing the calculation for 10 to 11 output bits. So if you think about the throughput of a biocell, it's much, much better. The problem is that the biocell, we cannot run Excel, we cannot do Office, we cannot play games. It's a different type of computing. But I'm comparing these two computing machines, and I'm doing this computing. If I want to generate 10 to 11 output bits, in a biocell, it will take 40 minutes. In silicon, it will take 66 days. So if you want to do biological computing, biological system, of course, cell is much better than silicon. If you want to play games or to read your email, silicon is much better. So what is the future? Still, the future is a system integration, and there are 4 factors. One is more transistors, 2D shrink, DTCO, and 3D integration. More memory, vertical integration, and dense 3D connectivity. More logic memory integration. We have chiplets, active on monolithic devices, and end-to-end optimization. So the simulation or the modeling, we need more software to go end-to-end simulation from the transistor to the full thermal management. So industry roadmap, what is the future? Energy efficient performance. Until 2012, we use what we call equivalent scaling, high K metal gate or strained silicon. Today, we use FinFETs, enhanced UV, extreme UV lithography, high mobility devices, and DTCO concept. So where shall we go? We hope that we keep going 2040 and go, we'll design 100 times better performance system. This is a wishful thinking. And with this slide, and this is the end of my talk. I think I'll go back to this slide. This is kind of a summary of my talk. This is the industry roadmap. I took it from TSMC. This is presented recently. And this is a very optimistic slide. Hopefully you guys and my students and your students will be able to deliver this technology. Okay, so this is it. And now I switch. I think I'll stop sharing And you can see me now in my office. I'll go back a little bit, and if you want to have questions. Oh, we grew up to 91 students, which is amazing. Thank you so much. It's really very good turnout, sorry. And we are now open to questions. If anybody has questions, we promised to have this lecture about up to 1.5 hours. So I kept about 10-15 minutes for question and answers. You're free to ask. Microphones are open. Raise your hand or just talk directly.
It is possible to
introduce yourself first.
I am Vazgen Melikan from Armenia.
Okay.
What do you think? What is the perspective of 3 nanometer GAA technology in sense of manufacturing?
I think it's possible. I think it's possible. For manufacturing, it's possible. The big unknown will be the yield and the cost and the profitability. But as I showed you some already, they already have prototypes and the proof of principle. But I'm very optimistic. Engineers, I have to tell you that when I was a student, I'm not so young, and I did my PhD with 1 micron technology. You can guess my age. And people talk about 1 gigahertz operation like nobody can do beyond it. And it took people like between 1980 to 2000 to break this barrier. And then I think that engineers at the end find solutions. And the solutions will come, the utilization. Your question is a very good question because it's a very deep question. It's not enough to make this technology. It will be useful if the designers will find the best way to design it and to make it useful. So it's not only a technology issue, it's also from the designer point of view, from not only the unit cell, but what kind of architecture is the best for utilization for this technology. I fully agree with you. I'm looking, it's a good question, but I don't know the right answer. I can give you my gut's feeling that technology is possible. Now the proof of, I would say the proof is on the engineers, and TSMC is one of the leaders in this field, and they have like unbelievable technology.
And can I give you the second question? Can you compare 3 nanometer GAA technology with 3 nanometer FinFET technology, conventional FinFET? Because in parallel, as I know, there exists also 3 nanometer FinFET technology, not GAA.
Okay, I have to tell you that all I can comment is what they publish. And actually, there are no good publication of the real performance of GAA versus FinFET. So unfortunately, I cannot give you a good answer to this. I'm waiting for them to publish more data to give you. Theoretically, GAA should be better, but theoretically and practically, sometimes are different. But you have to understand also that the 3 nanometer is the gate length. When you shrink your devices, you also increase the crosstalk and you increase other parameters. So it's not only the gate. It's also how do we package the device, how do we integrate the device, how do we do the metallization. It will be a very big factor in the final performance of it.
Okay, thank you.
Okay. I'll wait a few more minutes for questions. You can send it by, I see that. Okay, it's done. We reached 100, the magic number. We have 100 participants, 100 participants in this talk, which is absolutely amazing. It's 10:22. I think there's still people wishing to join the talk. which is, I think it's a little bit late, but if I'm right, I would like to thank Jacques Barocas, the local IT team at Tel Aviv University that made this broadcast available. I would like to thank all my friends in the NanoAL consortium. And if you have more questions, if you want some more inputs or outputs or discussions, you can send to my email. And don't forget that we are not only researchers in this field, we are also teachers in universities. And as I'm going to stress the conclusion that if you want to teach students to be good VLSI designers, we need to teach them technology and physics also. It's not only layout and computer science, it's also semiconductor physics. So, and of course, technology. Everything is integrated. So having said this, I would like to thank you all for the broadcast. And this is the end of this webinar. Thank you so much. And I hope to see you all in our next webinar, next talk, which will be published to the consortium members. And thank you. So
Prof. Yossi?
Yes.
Prof. Yossi?
Yes.
Sorry, before you leave. Anyway, I'm Alice. I'm from Malaysia. So me and about 17 of my students are here. So listening to your wonderful talk. Thank you very much, Prof. Yossi. Can you hear me? Sorry.
I can hear you very well. Thank you. I'm very happy to hear this.
Okay, sorry, yeah, because my internet connection is a little bit unstable. Just wondering, is this webinar is an annual event? So like, do we have another one sometime next year? So we would love to invite you to be the guest lecturer for my IC design class annually. Is that possible?
We have more lectures. You have to consult with Jacques and the head of, and also with the consortium. And you can, if you have, do you have my email?
Yes, I have your email, Prof. Yossi.
So send me email and we can send you. We have our, this is the talks under the consortium. We also have, by the way, other talks in this field that I can send you. And
okay.
I'm teaching this class, so we have my class lectures. And by the way, this lecture is the part of my, this is the last lecture of my regular class. I'm teaching VLSI design, and we have all the advanced VLSI designs and all. And we are changing the curriculum now every year. It's kind of, it's not an easy to be this class because it's and as you may know, in Israel, we have a very strong VLSI design industry. So we have all our students are easily get jobs in the industry, but we have to teach them very, we have to be very up to date because we cannot teach them all things. So we have to be every time up to date. But regarding your questions, we have more seminars, not only on these topics, on other topics also. And we can send you the list of seminars for the future.
Okay, sure. Thank you. I'll keep in touch with Jack then.
Yes. Jacques is our man. Jacques is the man. He's the, I'm only, he's my boss.
Okay. Okay, thank you very much.
Thank you. Good to hear you. Good to hear your voice. Thanks. Okay, guys. I think this is it.